the last video, we saw how a 2 by 2 matrix may not have an inverse, and it could therefore be referred to as a singular matrix. We also showed that we know a matrix doesn't have an inverse if an entire row on the left-hand side of the matrix goes to 0. This makes it impossible for us to turn that coefficient matrix into an identity matrix. Other interesting results can occur when considering a matrix and its solutions. We will simplify it into 3 different categories. Given any system of linear equations, there are 3 possible outcomes. First, the system has a unique solution, meaning there is exactly one value for each variable to make all the equations true and equal to each other. Second, the system has no solutions. There are no values that make all the equations true and equal to each other at the same time. Lastly, there are an infinite amount of solutions, meaning there's an infinite amount of numbers we can put in for our variables such that the equations are true and equal each other. Let's look at each one of these cases one by one. To demonstrate these, we're going to be using 2 by 2 matrices. This is because they're much easier to visualize, being lines on a Cartesian plane. If a system has a unique solution, the answer is where the 2 lines intersect. This is where the equations are equal to each other and their variables have the same values. So given a 2 by 2 matrix and its solutions, you can think about it as 2 different lines. And we know if it has a unique set of solutions if we're able to reduce the left-hand side to an identity matrix. So the unique solution for this system of equations is when x equals 2 and y equals minus 1. If the system has no solutions, it's because the lines never intersect. This means that the lines have the same slope but different y-intercepts. In other words, the lines are parallel. So how can we see this in matrix form? Well, remember, we can think of these matrices as lines. And if we rewrite them in y equals mx plus b form, we can see that they have the same slope but different y-intercepts. So if we were to use Gauss-Jordan elimination, we would see that one of the rows ends up being 0. However, on the right-hand side of that 0 row, it would be equal to some value. Here, that value is minus 1. So we have a statement that says 0 equals minus 1. And of course, this is a contradiction. Therefore, there are no solutions. If the lines have the same slope and the same y-intercept, then they're the same line. Since one line lays on top of the other line, then they intersect at all points, so there are an infinite amount of solutions. So how can we tell if there are an infinite amount of solutions just by looking at the matrix? Well, if we use Gauss-Jordan elimination, and we end up with an entire row of zeros, meaning on the left-hand side and on the right-hand side, then it implies that equation 1 is equal to equation 2. Therefore, they're the same line and intersect at every single point, so there's an infinite amount of solutions. Here's how we sum it up.